Assalamualaikum. Hello and good morning to Dr. Ainul and also Dr. Davendran. So today we from Group 8 will be presenting our reliability, ability and maintainability study on a gas processing plant. Alright, so I'll be introducing our Group 8 members. So and the first one we have Stephen, second Nur Shafarina, third which is me, Shaizim, fourth is Muhammad Arif Irfan, and lastly Muhammad Ali Sharizudi. So today I'll be presenting regarding the introduction of our project. So as you can see, the first thing first, we can go with the background. So we all know that gas plays an important role in providing energy, and high reliability and efficiency of gas processing plant is very important for all of us. And also because we're trying to processing gas, which means that our equipments need to have high availability, which will able to reduce the cost and increase the production and profit of the gas processing. But along the way, there are problems encountered in which the problem statements says that there are low usage of relative model in this gas processing plant. So in the sense where there are lack of utilization in terms of live data model to predict the plant's reliability. And also because of this, it makes us to be so unclear on what is the best course of action that we can do to increase the availability of this plant. Alright, so for the next part, which is the objective of this project, so number one is we need to develop RB diagram or reliability block diagram for the overall gas simulation processing plant and its processing equipment such as the turbine, compressor, pump, by using block sim for the analysis and simulation. And number two is to estimate the average availability of natural gas plant for 5 years based on the given failure time and MTTR, which is mean time to repair. And next is 3, to identify the critical equipment in the natural gas plant which significantly contribute to downtime and affect the overall availability figure. And lastly is to propose the action plans to be taken to achieve 99% availability with appropriate assumptions. And next, I'll pass it down to the next presenter.
Weibull++ software is a powerful tool used for reliability analysis, particularly in determining the distribution type and parameters of equipment within a gas plant. The first step involves collecting data from various equipment within the gas processing plant. Once collected, this data is entered into the Weibull++ software. Next, the software will allow for the fitting of live data into various distributions, for example, normal, log normal, Weibull, and exponential. Each of these distributions has its own parameter that will define its shape, location, and scale. The software utilizes statistical technique to fit the collected live data into this distribution. Next, once the live data is fitted into various distributions, the software will calculate the parameter for each distribution that fit the data. For example, for Weibull distribution, the parameters are shape parameter beta and the scale parameter eta. And for normal distribution, the parameters are mean and standard deviation. And for exponential distribution, the parameter is the failure rate. After fitting the data into various distributions and estimating the parameter, the software selects the distribution that provides the best fit for the data. This is typically done on statistical criteria such as goodness of fit test, likelihood ratios, and other relevant measures. Once the best distribution is identified, the software will extract the parameter of that distribution. This parameter represents the characteristic of equipment failure pattern within the gas plant. BlockSim obtains availability analysis through a simulation-based approach by using reliability block diagram, which is RBD model. First is to create RBD model. The RBD model will visually represent the system architecture and interconnection between the components. By constructing the RBD, we can identify critical components, analyze the impact failure on system performance, and assess overall system reliability. In creating the RBD model, first is to open BlockSim and create a new project. Second is to construct RBD by adding block representing different components or system in the gas processing plant. And lastly is to connect the blocks by using appropriate connection to represent the relationship between components. The second major step is to input model parameter. First is to double-click on each of the block in RBD to input model parameter. We can enter the model name, distribution type, for example, Weibull or exponential, model category, and its parameter. We also need to ensure that the units for parameter are consistent. For example, we are using days instead of hours. The third major step is to conduct corrective tasks. Corrective tasks represent maintenance or repair action performed on components to restore them to an operational state after failure or degradation. By setting up correcting tasks with appropriate duration, we can simulate the effect of maintenance activities on system reliability and availability. In this task, we need to set up corrective tasks for each component or system in the RBD. Next is to define the task duration to match the maintenance or repair activities associated with each component. We also need to ensure the task duration reflect the historical data or expected maintenance practice, which is as bad as old. The fourth major step is to link RDA equipment to live data equipment. By linking RDA equipment to live data equipment, it will enable us to incorporate real-life failure data into reliability analysis. By aligning the model reliability time with live data, we also ensure that the model accurately reflects the observed failure patterns and can make reliable prediction about future performance. This step, we can identify the components or system in the RBD that correspond to the equipment which live data is available. Set the model reliability time for this component or system to match the live data equipment, and we can also rename this component or system as U component to distinguish them from other blocks in the RBD. The fifth major step is to adjust the block properties. We can double-click on each block in the RBD to access its properties, change the block type from URD to U component to reflect the use of live data for reliability analysis, and ensure the operation and configuration of each block match the data provided. And last but not least, we also have to validate and analyze, which is reviewing the RBD model to ensure all parameters and connection are correctly specified. Validate the model to check for any errors or inconsistencies. Next is the last step, which is we can conduct reliability analysis by using block sim simulation capabilities.
Good morning, Doctor. My name is Steven, and I will be explaining about the discussion part of our project. First, let us look at the critical equipment ranking of the gas processing plant. We have listed out the top 5 critical equipment for both failure criticality ranking and downtime criticality ranking. So let us first look at the failure criticality ranking. A higher failure criticality index (FCI) means that the failure of an equipment is more likely to lead to system downtime or operational issues. Hence, it should be prioritized for maintenance and monitoring to ensure the system's overall reliability and availability. In this case, we can see that driver turbine accounted for 85.65% of the total index, followed by feed gas compressor of 1.58%, expander compressor of 1.57%, residual gas compressor of 1.55%, and lastly demethanizer of 1.07%. Hence, we can conclude that the driver turbine should be most prioritized for maintenance in this case. Next, let us look at the downtime criticality ranking. A higher value of downtime criticality index (DTCI) means that the component contributes the most to the total downtime of the system. This can be observed from the ETA value for the component, which is shown in the diagram below. ETA is the characteristic life for 63.2% of the equipment to fail. In this case, ETA value for driver turbine is 10.5 days, meaning that 63.2% of the driver turbine components will fail in 10.5 days. So for the DTCI ranking, we can see that driver turbine accounted for 47.95% of the total index, followed by demethanizer of 18.24%, generator of 4.02%, absorber of 2.52%, and core separator of 2.37%. Hence, we can conclude that driver turbine, demethanizer, and regenerator are determined as the most critical bad actors of the gas processing plant, and preventive action needs to be taken on these three equipment. Next, let us look at the overall availability of the gas processing plant. From the simulation run through BlockSim and Weibo++ software, we obtain the mean availability of 82.4%, meaning that in a 5-year operation, the total uptime will be 36,093 hours. For the downtime, it will be 7,707 hours.
Hi, my name is Arif Irfan. I will continue with improving the availability. In this project, we have calculated that the plant has availability of 82.4%. However, we need to investigate on achieving 99% of availability. So for that, we propose two actions. First, reducing the time to repair, and second is adding standby equipment. So for the reducing time to repair, here we have a table containing 7 critical equipment from the downtime criticality ranking. We have driver turbine, demethanizer, regenerator, absorber, code separator, filter separator, rich amine flash drum. To reduce time to repair, first we look at the data of the unit. For the value that is higher than the average, that value is reduced closer to the mean value. For example, for driver turbine, the old mean value is 0.6 and the new mean value is 0.37. The difference is 37.41% reduction. Once all new data is complete, we will put it in Weibo to calculate the log mean and standard deviation. Log standard. So for the adding standby equipment, here we have made two standby equipment for the regenerator and driver turbine. This extra equipment will operate once the main equipment is down, preventing the process from stopping due to equipment failure. After we did the simulation, the availability value is increased to 94.4%. This has affected the number of failure, previously 227, and now it is only 48 within 5 years.
Alright, now let's continue with the conclusion and recommendation part for this presentation, where it is based on a 5-year plant simulation that assesses the plant's reliability and availability. The simulation result achieved an average of 82.4% of availability, demonstrating a strong foundation for the plant's operation. However, there is always some room for improvements, and our analysis has identified the areas where we can optimize performance. One key takeaway is the impact of specific components on overall plant reliability. The driver turbine, for example, was pinpointed as a major contribution to downtime and failures. While its importance is undeniable, its current reliability presents an opportunity for improvement. But to truly unlock the plant's full potential, we've developed a series of recommendations that addresses the identified areas for growth. By implementing these recommendations, we aim to significantly enhance the plant's reliability and availability. The first one is to prioritize critical equipment. The driver turbine demands our immediate attention. We recommend a comprehensive reliability program for this crucial component. This program could encompass stricter preventive maintenance schedules, risk-based inspection, and redundancy measures. The second one is enhanced monitoring and control. Implementing enhanced monitoring and control system across all critical components would be a game changer. Real-time data on equipment performance would allow for a proactive maintenance, preventing unexpected downtime. The third one is risk assessment and mitigation. Proactive risk management is key. By conducting regular risk assessment, we can identify potential threats to plants' reliability and establish mitigation plans to address them effectively. The last one is invest in personnel. A skilled workforce is vital. Providing advanced training to maintenance personnel will significantly enhance the ability to diagnose and repair critical equipment, ultimately reducing repair time and ensuring effective maintenance practices. That's all for the conclusion and recommendation. Thank you.